Yeah, thank you very much for that suggestion. Then, so what we covered till now is we covered all the fundamentals of computational fluid dynamics, and we have reached to the stage wherein we should be able to solve Navier-Stokes equation for a simple lead-driven cavity flow problem. And once you solve lead-driven cavity flow problem, then you should be able to. I mean, then you will be essentially having a solver, and that solver can be used for different other problems, which are which essentially deal with laminar flow, because the methodology which we have seen is applicable to laminar flow only. So those who are interested to solve the turbulent flow, they are supposed to take up the course on advanced computational fluid dynamics. Those kinds of courses are also available in Atal Academy. So, uh, maybe you can do that. But then I thought on the last day I should take you through some case studies wherein the computational fluid dynamics techniques can be used to carry out the analysis and bring out certain physical understanding of the or certain flow physics when the flow is simple. Because many of us may be aspiring to do their PhDs, and for their PhD they require the tool like this, which is very important, which can actually bring out the essential physics in the flow and heat transfer phenomena. So from that point of view, I decided to go to share with you my own work, which is related with flow across multiple blood bodies, which is a case study which I did as a part of my own research, my own PhD work. So I thought I should share that. In the afternoon also, we will be having a presentation by Dr. Vinesh Gada, who will be also sharing the another application, another case study wherein the computational fluid dynamic techniques can be used. And then in the afternoon, we will be having at 2:30 we will be having a concluding session wherein Professor Malkhede, who is advisor to AICT, will speak about the uh, the essential role of teachers in the education. So let me begin with my topic. The outline of my presentation today is I'll be introducing my own research, that is on flow across multiple blood bodies. I'll be talking about objectives, blood body flow, a case study using CFD. I'll speak to for few minutes on lattice Boltzmann method. I'll spell out my research methodology. Then my work is essentially divided into four parts: flow around stationary row of square cylinders, flow around inline stationary square cylinders. Square cylinder is essentially a blob body. I'll talk about the definition of. I'll give you the definition of blob body as we go ahead. Flow around inline stationary square cylinders. And if time permits, I will also go through flow around maybe cylinders placed in a V formation, a cylinder around an array of cylinders, and flow around an array of cylinders, and flow around transferably oscillating row of square cylinder, and so on. I am not sure to what extent I'll be able to cover all these points because this is quite exhaustive. Uh, but I will try to give you at least first two, the, the, the details of the first two works which we have done. Uh, so what is blob body? Blob body can be defined as a body that, as a result of its shape, has a separated flow over a substantial part of its surface. So if there is a simple body placed in the flow, and if flow occurs over that body with a certain Reynolds number, it's not that the flow is always the fluid is always in touch with the surface of the body. The fluid gets separated from the surface of the body, and this separation phenomena is very important, which leads to development of the forces experienced by the body because of flow. These forces may be classified as the forces in the direct force experience in the direction of the flow, which is called drag, and force experience in the direction normal to the flow, which is called lift. So any body which is when kept in the fluid flow, the fluid does not touch the whole boundary of the subject, and because of which some kind of a wake formation takes behind the body. You must have seen a car running on the road. At the back end of the car, sometimes there is a flap provided. That flap provides the flap actually helps the to have a better separation, and that helps to reduce the drag which is experienced by the car. Drag is nothing but its resistance to its motion. So essentially, I mean, the body is said to be bluff when the separation is over a large part of a surface of a body. Uh, for example, if you have an aerofoil shape, aerofoil shape is it's a streamlined body. If the flow is occurring over the aerofoil, the flow is in touch with the surface of the body over a substantial part. So aerofoil is usually called a streamlined body. But if it is a square plate, square body, or even if it is a cylindrical body, then such a body is essentially called a bluff body. See, for example, flow around a single square cylinder. When the flow occurs around a single square cylinder with a very low Reynolds number of the order of, let's say, 1, it occurs like this. I mean, the flow comes to the body, it is in continuously in touch with the body, and even at the back end of the body, it touches the body, it touches the surface. So essentially, there is no separation occurring here. However, if my Reynolds number is of the order of 2 or 3 or 4 or 5, you will find some kind of vortices are developed behind the body. And the flow, when it comes around the body, it goes over the vortices. It goes over the vortices. So here also the separation has not occurred. When it goes to, our Reynolds number goes to 40, the size of the vortices has increased. But when your Reynolds number is 50, you can see the flow actually separates from the surface, and there is good amount of velocity gradient developed on the surface, and that gradient of velocity develops the vorticity. That vorticity is accumulated behind the body, and this vorticity, when this vorticity, the amount of vorticity accumulated is very high, this vortex actually is shed from the body. It leaves the body. This phenomena is called a vortex shedding, and the phenomena in which the fluid actually detaches from the body is called separation. So at Reynolds number of 120, Reynolds number of 180, the vortex shading is always observed. As the Reynolds number goes on increasing beyond 50, uh, the the vortices are developed alternatively at the top end and the bottom end, bottom rear end, top rear end, and bottom rear end of the body. And these vortices grow in size, and at certain point of time, these vortices detach from the body and go into the main flow. Such a flow is called uh, the the vortex shading. You can see this vortex shading through the small movie. See, when the flow is occurring over a body, there are vorticity gradients developed. These vorticity gradients develop the velocity gradient. Sorry, these velocity gradients develop the vorticity, and that vorticity then goes into the main flow. I mean, one vortex is shared from the bottom, another vortex is shared from the top. One vortex is shared from the bottom, and another vortex is shared from the top. So this vorticity, this vortex shading occurs with a certain frequency, and the frequency is called a frequency of vortex shading. And this frequency of vortex shading many times is expressed in terms of uh, parameter called Strouhal number, which is a non-dimensional vortex shading frequency. If the frequency is multiplied by characteristic length and divided by characteristic velocity, for example, f is a frequency. If it is multiplied by the diameter of the cylinder and divided by the incoming velocity, then what we obtain is a non-dimensional parameter, and that non-dimensional parameter is called Strahal number. I have not mentioned the Strahal number here, but it's a Strahal number. Similar kind of thing you can see vortex shading phenomena. I'm just sharing with you the another movie. This work is essential. This work is actually carried out by Sachin B. Paramne and Professor Atul Sharma at Indian Institute of IIT Bombay. But it's possible to develop such kind of movies in computational fluid when we make use of computational fluid dynamic techniques. The movies are uh, prepared using a software called TechPlot. This indicate essentially the streamline pattern, and streamline pattern at different time instances is captured, and we get the we can then observe the phenomena of a vortex shading. You can see the vortex grows, and then it goes into the main flow. It is actually shaded, and then once this goes bigger, the another vortex starts developing here. So this is what occurs in case of a bluff body. Now, if you look at the various variation of the forces experienced by the body, then we can I am sharing with you here the result given by Professor Sharma and Iswaran, that with increase in the Reynolds number, your drag force goes on reducing, because with increase in the Reynolds number, your inertia force increases and viscous force decreases. Viscous force decreases substantially, and hence the drag experienced by the body decreases. Here is a result given by for recirculation length. If you look at this particular, the recirculation length is nothing but the length of this vortex within which the recirculation is occurring. If you observe here, with increase in the Reynolds number, your recirculation length it goes on increasing. This has been shown up to Reynolds number of 40 only, because beyond Reynolds number of 40, we observe the vortex shading phenomenon. So this is recirculation length goes on increasing. The result is compared with that of the literature also, and the similar kind. I mean, the increase in the recirculation length is observed even for circular cylinder. Here are the results, variation of a mean recirculation length and Strahl number with the Reynolds number. So recirculation length for other Reynolds numbers is also given. I mean, the region in which the recirculation occurs keeps on decreasing with increasing the Reynolds number beyond 50. And then beyond 50, the vortex shading frequency is also developed. So with increase in the Reynolds number, you can see the frequency of vortex shading goes on increasing. The results are compared with the experimental and numerical result by others also. The Strahl number here is now nothing but it's a vortex shading frequency. See, at Reynolds number of around 100, we get the vortex shading frequency which is of the order of 0.145 or about 0.148 around it is. That's a value for RE equal to 100. So at Reynolds number of 100, my Strahl number for a simple square cylinder is of the order of 0.148, which is nothing but this Strahl number is nothing but the frequency of vortex shading. This frequency of vortex shading is very important to us, because with change in the frequency of change in the vortex shading frequency, the nature of the forces experienced by the body changes. We will see that in due course of time. You can see with increase in the Reynolds number, there is always reduction in the drag coefficient. I mean, these results are provided for Reynolds number up to 150, but beyond 150, the flow becomes three-dimensional, and hence the results are not captured using because these results are captured for the laminar flow, and beyond 150 or so, beyond Reynolds number of 150. In case of a flow around cylinder, the flow becomes three-dimensional, and beyond 200, it becomes turbulent. Here, the results are provided for lift coefficient in terms of RMS, its RMS value. can see the RMS value of a lift coefficient also goes on increasing with Reynolds number. So that's something about a single flow around a single square cylinder. Our objective is to go through flow around multiple square bodies. But I will come to that. I thought I should give you the background of, because single square cylinder is an extreme case of multiple square cylinder flow around. We are going to look at large number of multiple square cylinders. So this is one extreme, and that is another extreme. I thought I should provide you some details of the first extreme. So our objective in the present lecture is to present you a case wherein it is emphasized that a CFD technique can be well adopted for PhD research even without going through the complexity of mathematics. That's the objective of my lecture, what I am going to present you. And the other objective is to demonstrate the use of a simple tools learned during undergraduation education for carrying out the in the process of going through this particular session. You will also understand that the simple mathematical tools which we studied during our 12th standard and undergraduate program, those can be very well adopted uh, for carrying out the research. So let's go around. Let's look at flow around multiple blob bodies. Flow around multiple cylinders is an important structural design problem. In many situations, you will find that there are multiple bodies kept. Just take the pillars of the bridge, which river bridge. There are plenty of pillars in the river which experience the forces. Flow around single cylinder is a classical problem. The one which we have seen just now is a classical problem which people are studying since last maybe 100 or 200 years. But when there is a adjoining body present, it alters the vortex shading and wave formation phenomena. This is what we are going to understand, how it alters. If there is another adjoining body, that adjoining body actually disturbs the vortex shading phenomena. And how does it disturb? That we will try to understand. Flow behavior around multiple bodies is different than flow behavior around two bodies. I mean, when there are two bodies, there is ample amount of space for fluid to flow around. But when there are large number of bodies, the space for fluid to flow around is very less, and that actually creates a lot of disturbances in the wake pattern or the vortex shading pattern, and it alters the nature of the forces experienced by the body. And those forces, especially when the problem is a structural design problem, the forces are important to us, and hence we will be looking mostly at the forces. The relative geometric position of the bodies, such as rho, inline, V formation, alters the flow patterns and the parameters substantially. So flow patterns and flow parameters like drag experienced by the bodies, then lift experienced by the bodies, that is altered substantially when we change the geometric positioning of the bodies. Like if the bodies are kept in vertical row, if the bodies are kept in inline rows, or maybe in other geometrical positions, the the nature of the forces experience changes. So wake interaction and interference in such a cases poses a challenging fundamental problem. How the wake interact with each other, and if the wake is interfered, how does it affect the nature of the forces? That has to be looked at. I'm just sharing with you the motivation. There are plenty of situations wherein there are multiple bodies. See, flow around the pillars of the bridges. There are lot of blob bodies and all these blob bodies will experience the forces. This is a nuclear reactor. In nuclear reactor, there are a lot of horizontal. The bodies are there, tubes are there over which the flow occurs. The buildings also experience the wind load. If we have the adjoining building close to each other, these buildings will experience the wind load. Again, the cars moving on the express highways. Let me tell you a simple thing. If I have one body over which the flow is occurring, I experience, let's say, X amount of drag. And if there is another body which is very close to the first body, and then the flow is occurring, the drag experienced by both these bodies is almost 10 times that of mm, the single body. So you can imagine the significance of an adjoining body. So if you have a building here, independent building will experience certain amount of drag, a certain amount of force, wind load. But the moment there is an adjoining building very close, the wind load will increase maybe by tenfold or so. So that's the significance. That's the motivation why we should understand flow around multiple bodies. The other motivation is that there is a lot of qualitative. The qualitative behavior is revealed through lot of studies. I mean, there are some study by Weaver and Zdravkovic. They have provided the qualitative behavior by carrying out certain experiments. They have just given some pictorial or photographs are available. However, there is a lack of quantitative evaluation and sufficient measurements. The measurements are rarely available for multiple block bodies. Then Simonin and Babalani, Ian Skesi, many people have obtained the velocity field. However, there is lack of data close to the cylinder. It's not possible for when you carry out the measurements, it's not possible to obtain the velocity at each and every point, which is possible in CFD. And because the data is not available, we thought we must capture the data using computational fluid dynamics techniques, and then we should analyze the flow. So the overall objective is to substantially study the flow around square cylinders, which may lead to a physical model that can predict the flow behavior for a given flow conditions and geometric configurations of the cylinder positions. The other objective is to identify different flow regimes. We will look at these flow regimes as we go ahead to identify different flow regimes, modes for a given flow conditions and configurations. The moment I change the configuration, my flow regime may change. That is what we will look at. We'll also try to understand the mechanism of wake interaction, oblique interference, oblique wake oscillation, and its effects on the regimes, flow regimes, and flow parameters. So the moment there is another body, there will be two. Say we have one body, there will be having one wake. We have another body, there will be another wake. And when these two wakes interact with each other, that interaction actually affect the nature of the forces experienced by the body. And that's the important thing which was not reported in the literature, and we try to bring out that those phenomena of wake interaction in this work. The other objective is to verify the results of stationary cylinders with the help of study of flow around transversely oscillating cylinder. I'm not sure whether I'll be able to cover this particular topic, but definitely I will be able to cover the first three topics, first three objectives. Problems which we have addressed are the first one is cylinders are kept like this and the flow is occurring over it. This problem is called row of cylinders. D is the dia and S is the spacing between the body. D is the size of the body and S is the spacing between the body. So this particular configuration is called row of cylinder. Then the bodies are kept in the horizontal position and the flow is occurring over it, and the distance between two is S again, size is D, and this particular configuration is called inline cylinders. I'll be focusing mostly on these two configurations. Maybe I will not be able to focus on the V configuration, V formation configuration of a V formation. We have also worked with array of cylinders like this, wherein this is my streamwise spacing and this is my transfer spacing, which we change, and we also change the Reynolds number and try to understand what happens to the wakes and how the wake interaction takes place. So what we did, we have used a simple methodology called Lattice-Boltzmann method. In Lattice-Boltzmann method, a kinetic equation for a particle velocity distribution function is solved. I am not going to take you through the details of Lattice-Boltzmann method. Let me tell you one thing: Lattice-Boltzmann method essentially solves Navier-Stokes equation, and there is a mathematical proof available in the literature for this. My objective is not to take you through the Lattice-Boltzmann method. I have used Lattice-Boltzmann method, but you can use finite volume method to solve this particular problem. So even finite volume method, with finite volume method also we solve Navier-Stokes equation. With Lattice-Boltzmann method also we solve uh, the Navier-Stokes equation. And through both the methods, we obtain velocity distribution, pressure distribution, which is important to us. And once we get velocity and pressure distribution, we can find out the drag coefficient, lift coefficient, and so on and so forth. And even Strahl number as well. So in Lattice-Boltzmann method, I will tell you this method in a nutshell. The kinetic equation for particle velocity distribution function is solved. Evaluation of the system from one time step to next time step. The successive propagation and collision steps take place. In fact, there are certain nodes, and every 44 fluid particle is considered as a node, and then there are adjoining nodes, and then discrete velocities. There are certain models available. For example, if this is for two-dimensional, there are 9 nodes which are used in the methodology. So D2Q9 model on two-dimensional square lattice is used. The obstacles in this particular method, the most important thing is that there are two types of step. One is a propagation step, and the another is a collision step. So what is the basic fundamental of a Lattice-Boltzmann method is that when two particles collide over each other, then they after collision they propagate. So before the collision and after the collision, the momentum is conserved. That's the fundamental concept we use in Lattice-Boltzmann method. The beauty of this Lattice-Boltzmann method is that it is easy for us to introduce the obstacle in the flow. Obstacle in the sense, in our case, though it is easy to introduce the bluff body in the Lattice-Boltzmann method, and that is why we prefer to make use of Lattice-Boltzmann method. In finite volume method, it is really difficult to generate the grid for the moment you change your configuration. I mean, every time you need to change the grid. Here, it's very easy to carry out the grid generation and introduce the obstacle in the flow. These are some of the equations which I will not be going through the details, but this is a discrete kinetic equation for the particle distribution. Then the equilibrium density function is computed like this. These equations are well discussed in the literature. There are books available on Lattice-Boltzmann nowadays. This method is widely used by the researchers for carrying out resolving the fluid flow and heat transfer problems. Then the velocity and pressures are calculated by using these equations. So I don't want to take you through the detailed mathematics again, but I want to focus on my work. The research methodology which I have followed here is that we did a systematic validation of Lattice-Boltzmann method based code. We developed our own code for solving problem around multiple block bodies, and we did the systematic validation which I will share with you. Then we carefully study the lift and drag coefficients of signals. We obtained the signals for lift and drag coefficient, and we carefully studied those. We also did the power spectra analysis of the time series of lift and drag coefficients. So whatever the signals we obtained, we carried out the power spectra analysis for that. Of that. Then we also looked at the vorticity contours and wake patterns. Based on above study, different flow regimes were identified and flow parameters were obtained. And we carried out the regression analysis to obtain the expressions, mathematical expressions for drag coefficient and lift coefficient and Strahl number. And finally, the physical description of different flow phenomena have been offered along with evidences. We did that. So let us come to the first part. We use our code for the validation purpose. We varied the Reynolds number and tried to obtain the Strahl number for different single square cylinder case. And then you can see the present results are shown by dark square symbol, and other results by Sharma Iswaran, Ravichok, and Norberg, which are available in the literature. Those are plotted here, and you can see there is a fairly good matching of a variation of Strahl number with that of Reynolds number. With increase in the Reynolds number, the Strahl number is increasing. Here also you can see with the increase in the Reynolds number, the drag coefficient is changing. We have compared our result. Present results are shown with the dark uh, symbol here, and the other results are the unfilled symbols. Sharma, Iswaran, Sewatkar, and Frank. You can see more or less there is a close agreement between the drag which is obtained for single square cylinder. That was the quantitative validation for single cylinder. We also did the validation of a code for to do the qualitative comparison of vortex shading from the cylinder. These results were available in the literature, but these results are of course available for square bodies. These are the actually experimental visualization results obtained through experimentally obtained through the visualization. The results were given by Mizushima and Akinaga. You can see the vortex shading is occurring behind all the cylinders. The essential phenomena of vortex shading is also captured by us, and this indicates that we are able to capture the essential phenomena of vortex shading around all the bodies. So this is just a call. Although the nature of the cylinder or form of the cylinder is different, these are square, these are circular, but we are also able to capture the similar phenomena although our bodies are square in shape. We have also compared our results with that of the results available in the literature given by Kobayashi. He also did some flow visualization. So we compared our results by drawing the flooded contours. These are line contours of vorticity. These are flooded contours of vorticity. We are also able to capture the essential phenomena of flow around multiple bodies. See here also the bodies are circular in shape. We further did the validation of the code by considering flow around a single oscillating square cylinder. The cylinder is oscillating like this. It has got a certain forcing frequency. With certain forcing frequency, it is oscillating, and the flow is occurring over it. Flow is occurring over the oscillating cylinder. If that is the situation, this forcing frequency can be expressed in terms of a forcing frequency ratio, wherein Fe is the frequency of forcing and FO is the frequency of vortex shading when my cylinder is stationary. So Fe by FO is the forcing frequency ratio. FO is the frequency of vortex shading when my cylinder is stationary, and Fe is the frequency of oscillation. So this normalized ratio is varied as 0.5, 1.8, 1.2, 1.5, and the results were available in the literature by results were given by Singh et al. Their numerical results indicate values for 1.5, 1.52, 1.9, and 1.87, and we also obtained the similar kind of values. So this indicates that we were able this indicates that the lattice-Boltzmann method can be well adopted for solving the problems of flow around multiple bodies. We also compared our results with that of the experimental results available in again forcing frequency ratio was varied over a large range. I mean, it was the simulations were carried at large number of forcing frequency ratios. These are the present results, and here are the results provided by Tanida et al. 2008. Their results are experimental results, and we have very close matching or the agreement between the two results, which again further this all gave us the confidence that we can use lattice-Boltzmann method. We can use our code for rigorously. We can use our code for complex problems of fluid flow, like even because we have even validated the code for oscillating body. We further did the validation by using flow around two oscillating square cylinders. These results were available in the literature. These results are by Mahir and Rockwell. They did use two circular cylinders, then oscillated those cylinders with certain frequency, and then tried to visualize the flow. We also did the same thing. You can see there is, this is again of course the qualitative comparison, but then qualitative comparison as well as quantitative comparison both should go in hand, and that has helped us. That this has also given us the confidence that the even for the oscillating flows also we can make use of the lattice Boltzmann method, our own code. So this is a qualitative comparison. So that's what we have done. We have done rigorous validation. You can see for single cylinder, stationary cylinder, for multiple cylinders, for single oscillating, again single oscillating, and then for two oscillating. So we have carried out good amount of validation of our code. Rigorously, the code is validated, and then we develop the confidence, and then we started using our own code for different configurations. First configuration which we dealt with is a flow around row of stationary square cylinders. Row of stationary square cylinders. This work we published in the journal titled Physics of Fluid, which we did present in published in 2009. So the configuration is something like this. There are large number of cylinders placed. I mean, although we have restricted ourselves to 9 number of cylinders, C1, C2, C3 up to C9, but what we have done here is that, and the flow is occurring on all these 9 cylinders. The size of the cylinder is D. The spacing between these are equispaced. The spacing between cylinder is S. What we have done, we have used here the periodic boundary conditions. What is periodic boundary condition? So whatever is the velocity, whatever are the velocities at this boundary, the same velocities are experienced here. Such a boundary conditions are called periodic boundary condition. Why does it happen? Because the phenomena which is occurring here, if the same phenomena, I mean, if I have an infinite number of cylinders, let's say, if I have infinite number of row of cylinders place, then my fluid flow phenomena is bound to repeat after certain transverse distance. It's bound to repeat. But if we have small number of cylinders, that repetition may not occur. If we have, let's say, 3, 4, 5 number of cylinders, it may not occur. But it may repeat. The phenomenon may repeat if I have a large number of cylinders. But large means how many? 9, 10, 11, 12, 13. How many cylinders shall I take? I need to restrict somewhere so that I can do the simulations. So what we did, we considered 10 cylinders, 9 cylinders, 8 cylinders, 7 cylinders, 4 cylinders. And we tried to capture the mean drag experienced by each of the cylinders. And then we found I consider only 4 cylinders, I get this much of drag. 7, I get this much of 8, this much 9. So we observed that when my number of cylinder goes beyond 7, 8, 9, there is hardly any variation in the drag experience. It means the phenomena is now repeating. So we arbitrarily decided to take 9 number of cylinders and implement the periodic boundary conditions. Of course, for 4 cylinders also we implemented the periodic boundary conditions, but with 4 cylinders, the phenomena is not repeating. That is what we concluded from these results. So this is a small homework which we did. So we deployed the periodic boundary conditions. So whatever the velocities are here, those velocities are assigned here, and whatever the velocities are here, those are assigned here. So essentially the phenomena is repeating. On the surface of the cylinder, we implemented no slip boundary condition, and at the inlet we have provided uniform flow profile on the upstream boundary. That is, u is equal to u naught or u is equal to u infinity. There is no v velocity. At the exit, we have employed a convective boundary condition. Convective boundary condition is given something like this: del u by del tau. I mean, I am using here fi because I am using lattice Boltzmann method. But if it is a finite volume method, I can have boundary condition like this: del u by del t plus UC is the average velocity here. UC plus del u by del x, del u by del x, that is equal to 0. So this such kind of a boundary condition is called a convective boundary condition. It helps you to reduce your computational domain by a substantial amount, and that helps us to carry out the simulation little faster if your domain size is reduced. Then this is LU is the upstream distance, LD is the downstream distance we have taken. We have also carried out the domain independent study. I mean, we have varied the domain size and we have tried to capture the values of drag coefficient and lift coefficient. And then we finally decided the domain size. This LD is taken as around 20 times that of the size of the cylinder. LU is taken as 7 times that of the size of the cylinder, and so on and so forth. So this is something about, this is essentially a problem definition and numerical details of the details. Numerical details of the problem I have tried to explain. This is my bottom boundary, this is top boundary, this is an upstream boundary, and this is downstream boundary. We also carried out literature survey. So it was observed that not much attention has been paid to the row of square cylinders, which represents the other extreme of a single cylinder, as I said at the beginning. With numerical models, researchers have obtained transitions in the flow. And the information about flow field is limited. When I say flow field, I mean to say velocity information at large number of points around the body that is not available. Maybe at 1 or 2 points people did the measurements, but the results, the velocity field or pressure field was not available at large number of points. Kumar et al. In 2008, he explored different flow regimes at single Reynolds number, but the changes in the flow regime with different Reynolds number is also of interest. Then variation in the wake size was also talked about by few researchers, but then the merging of, and then people also talked about merging of jet, but then actual wake interaction phenomena was not is not explored by the researchers. So our objective is therefore to go beyond their viewpoints. Whatever is reported in the literature, we wanted to go beyond that, and we try to obtain the combined effects of spacing between the cylinders and Reynolds number on flow regimes and flow parameters that have been brought out in the present work. What we did, we varied Reynolds number between 30 to 50 in the step of 2 and 60 to 140 in the step of 20. I'll tell you why this kind of range has been taken. And S by D is changed from 1 to 4 in the steps of 1. S by D is a non-dimensional spacing between two bodies. And limited simulations were also carried out S by D equal to 5. So total number of 40 simulations we carried out. Let me tell you, one simulation in this case takes more than 4 to 5 days. And if the Reynolds number is high, of the order of 140, it took more than 8 days for one simulation to obtain a substantial amount of data which can be used for the purpose of analysis. So to begin with, what we did, we tried to understand the effect of spacing on the steady and unsteady flow. The flow is steady. What I mean to say, when the flow is occurring around the bodies, the flow is occurring around body, we consider a certain point, and we try to track the velocity at this point. This velocity does not change with respect to time. It means my flow is steady. If it changes with respect to time, my flow is unsteady. So where the transition from steady to unsteady occurs, that we have tried to understand through a bifurcation analysis. We carried out the bifurcation analysis. Bifurcation analysis is one of the important tool available to us, all of us. We have studied this bifurcation analysis as a part of our undergraduate mathematics. In this bifurcation analysis, what we did, we considered this point, we track the velocity. When my flow is unsteady, my velocity changes like this. It changes with respect to time sinusoidally. When my flow is steady, the velocity, there is no variation in the velocity. It's not zero here, it's a small velocity is there. It remains constant. It does not change with respect to time. On x-axis, I have time here and here. This is for r equal to 40. This is for r equal to 37 we have shown. So at r equal to 37, it is steady, but at r equal to 40, it is unsteady. It means between 37 and 40, there is a critical Reynolds number at which the flow transits from steady to unsteady. So what we did simulations at different Reynolds numbers. Maybe we did it at 37, then with the steps up to 39 and so on and so forth. 37, 30, maybe 40, 42, 45, and so on. And we plotted the symbols, the maximum velocity in positive y direction and maximum velocity in negative. This is a v velocity, that is velocity in the y direction is plotted here. We captured what is the value of maximum velocity, maximum positive velocity, and maximum negative velocity. It changes around it changes around 0. So this is maximum negative, this is maximum positive. And then we plotted a curve between these two using this expression, which is the expression of Hopf bifurcation available in the literature. And wherever it intersects that of the x-axis, that is my critical Reynolds number. So 38.38 is the Reynolds number for when my S by D is 4. 38.38 is the critical Reynolds number at which the transition from steady to unsteady occur. And I have shown these two figures to provide the evidence for that. That at 37 it is steady and at 40 it is unsteady. So such precise result was not available in the literature, and hence around this particular Reynolds number the transition occurs. We actually we also looked at the variation of critical Reynolds number with spacing for the onset of. So it must be understood that this is the Reynolds number beyond which the vortex shading occurs. Below this, there is no vortex shading. Why vortex shading occurs at such a location, at such a Reynolds number? Why? What so specific occurs at such a Reynolds number? That was the critical question asked by the researchers to us, and we developed the thought process for that, and then we published that thought process in the journal Physics of Fluid. The thought process is that below this Reynolds number, the rate of vorticity generation is low, and that vorticity can be transported merely because of a diffusion. Vorticity transportation takes place because of diffusion. But at a certain Reynolds number, the rate of vorticity generation goes to it passes such a limit that my diffusion is no more capable to transport the vorticity, and thus convection sets in, and that convection causes the vortex shading. That's a physical thought which we provided to this bifurcation analysis, and because of that setup of because the convection is set, because my diffusion is no more capable to transport the vorticity, the convection sets in, which leads to vortex shading. So we also tried to explore the vortex shading phenomena for multiple cylinders through the use of a bifurcation analysis. Further, we plotted the wakes behind bodies. What is wake? Wake is the region behind the body in which the x direction velocity is less than the incoming velocity. So this black region indicates the region where u velocity is less than that of incoming velocity or free stream velocity, we call it. So now you can see we work with a certain Reynolds number, let's say 100 or so. 80, Reynolds number of 80 we work. S by D is 5. You can see all the wakes are behind the cylinders are independent. They are not interacting. They are not. There is no interaction between these wakes. But the vortex shading is occurring. The wakes are not even touching each other. What happens because of this is that the lift coefficient varies sinusoidally. I will show you. See, in that case, my lift coefficient varies sinusoidally. Pure sinusoidal variation is there. This is the lift coefficient plotted against time. When I reduce the spacing to, let's say, 4, we did simulation for S by D more than 5 also. The wakes are independent. But when S by D is 4, you can see there is a structured interaction between wakes. These wakes are interacting with each other. These gaps, which I have designated as G9, G8, G7, and so on, these gaps at one time instant are closed, at other times instant are open. This is closed, but here see it is open, this is closed. So these gaps keeps on closing, opening, and you see the systematic structure of a wake behind the body. This systematic interaction of the wake behind the body leads to modulation in the lift coefficient signal, and that modulation is also systematic. I will show you. The modulation are there. So here in the signal there is only one frequency. Here in the signal we have two frequencies. One is the frequency of vortex shading, and another is the frequency corresponding to these two peaks. These two peaks. So there are two frequencies. This second frequency, we have termed it as a secondary frequency. And when there is a flow, and the thing is that the time period of two consecutive cycle is constant in this flow. The time period of two consecutive cycles is constant. Here, if I take the two consecutive cycles of vortex shading, small cycles are there. The time period is changing, but it is changing hardly within 10%. However, if I take the time period of the secondary frequency, this time period is not changing for the consecutive cycles. So there is a secondary frequency, but the time period of a secondary frequency for consecutive cycle is constant. However, the time period of a primary frequency for consecutive cycles is not constant. It is changing within 10%. This flow we designated as a synchronous flow. This flow we designated as a quasi-periodic one flow. When I further reduce the spacing between two bodies, it is seen that some of the wakes are broken. Some of the wakes are broken. And that leads to further alteration in the or further modulation in the nature of the forces experienced by the body. We have shown here. See, now here this secondary time period, I mean, although the flow is periodic in nature, but this secondary time period which was constant here is no more constant in this case. Excuse me for a second. Still, the secondary time period is no more constant. When I reduce the spacing further, you can see there is more breakage of the wakes. When I reduce it to 1, the entire wake structure is broken. See the wake structure, how systematic it was. Here all the wakes are independent. Here we get a systematic wake structure. The wake structure has slowly broken. It has broken, completely broken when my S by D is 1. So such a flow, I can call it as a chaotic. When it is slightly broken, we designated it as quasi-periodic 2. This is quasi-periodic 1. So what is the essence in synchronous flow? The time period of a primary cycle, consecutive cycles is same. In quasi-periodic one, the time period of consecutive primary cycles is varying, but it is varying only within 10%. And the time period of a secondary consecutive cycles is constant. In the quasi-periodic 2 flow, the time period of secondary consecutive cycles is also varying. Primary is varying, secondary is also varying. Here primary is constant, here primary is not constant, but secondary is constant. Here primary, secondary both are constant, and here the signal is completely chaotic. And that is happening because wakes are independent, wakes have structured interaction. Few wakes are broken, all the wakes are broken. So the moment I keep on reducing the spacing between the cylinder, the wake structure completely breaks, and that leads to a chaotic variation of the forces. And I am just sharing with you here. It is. Give me a second. See the structure variation. See the interaction of the wake is systematic, and this systematic interaction in the wake actually leads to modulation in the frequency experienced by the cylinders, forces of the cylinder, but that those modulations are also systematic. I can say the flow is periodic in this case, although it is unsteady. Here I am just sharing with you the variation in the vorticity. This is the vortex shading occurring behind multiple cylinders. So these are the movies which we have created after capturing data at a large number of time instances, and all data is loaded in a single file. And using a software named TechPlot, we can create such kind of movies to understand the flow behavior. So here I have non-interacting wakes, which leads to synchronous flow, structured wakes, which leads to quasi-periodic flow, breaking of wake structure starts, which leads to quasi-periodic 2 flow, and completely broken wake structure, which leads to chaotic flow. We have also carried out the power spectra analysis for synchronous flow. For synchronous flow, we get only one frequency in the power spectra, but when the flow is quasi-periodic 1, we get two frequencies. This is my synchronous flow. I have only one frequency. The Strahl number is of the order of 0.180. This is for S by D equal to 4 and R equal to 140, sorry. This is S by D equal to 40 and R equal to 80. So you can see, even with increase in the Reynolds number also, we can get, and this is at the same spacing, but Reynolds number is different. We have a synchronous flow. We have looked at the effect of Reynolds number also. We have varied the Reynolds number. Here we have two frequencies. There is a small peak in the power spectra. Power spectra is nothing but it is the fast Fourier transform which we have taken to obtain the number of Strahl numbers which are significant Strahl number, or number of capture the significant frequencies in the signal. So for quasi-periodic 1 flow, we have secondary frequency in the flow. Based on our results, we have defined the flow regime. The flow regimes are defined like this. We have varied S by D, we have varied The Reynolds number, you can see if my Reynolds number is high and spacing is high, then I obtain synchronous flow. For low Reynolds number, I obtain quasi-periodic 1, and of course, uh, the S by D is also on the larger side. But for S by D equal to 2, I get quasi-periodic 2, and for S by D equal to 1, I get chaotic flow irrespective of Reynolds. That's a that's a that's a flow regime map which I have plotted. I hope I am audible to all of you.
Yes, sir, you are audible.
Yeah, the presentation is also visible clearly, right?
Yes, sir.
The presentation is also visible clearly, I hope.
Yes, sir.
Sir, yes, sir.
So this is the flow regime map. I am just summarizing the flow. The synchronous flow is no significant interaction of vortices. Time period of consecutive vortex shading cycle is constant, and there is no secondary frequency. That's the synchronous flow. Quasi-periodic one, vortices interact in downstream region. Secondary frequency is present. Variable time period of a primary and constant time period of a secondary frequency. Quasi-periodic 2, substantial lateral movement of vortices. Variable time period of a primary and secondary frequency. Both are variable. Here only one is variable. Here is nothing is variable. I mean the frequency time period is not variable. It's time period in first case is variable. Time period in secondary frequency is so primary and secondary both is variable. And in chaotic there is a haphazard motion of vortices with no relation between shading from different cylinders, and no clear peak in the spectrum is seen. Second important problem which we looked at is the flow around inline stationary square cylinders. The work is actually published in Journal of Fluid Mechanics, although I have written it under revision. That time it was under revision when I prepared this presentation. So the configuration is now like this: C1, C2, C3, C4, C5, C6. We work with large number of cylinders also, but then we finally decided to go ahead with 6 number of cylinders, as there was no variation in the results. Again, uniform flow profile on the upstream boundary. There is no slip boundary condition on the surfaces, convective boundary condition at the lateral edge, and a free slip boundary condition on the lateral boundaries. Here we assume that there is a boundary, but it's not a wall. So such a boundary condition is called free slip boundary condition, which we adopted here. We carried out the literature survey. We found that most of the work is on two inline cylinders, with a major focus on understanding the forces experienced by the cylinders, and the negative drag on the second cylinder was reported. Especially Mittal et al. And Carmo et al. They work on that. So negative drag was reported. Different flow modes were also proposed depending on the spacing. A single bluff body shear reattachment. Our research method identifies additional mode. We have identified 4 different modes. Earlier, only 3 modes were identified. The hysteresis is accompanied by discontinuous jump in the mean drag. Is reported for progressive increase or decrease in S by D. That is also reported. We have seen. Onset of a vortex shading at Reynolds number of 35 to 40 is reported for S by D smaller than 5. For single cylinder, it is 47 plus minus 2, which Sharma Ixoran has reported. 6 inline circular cylinders were also reported in the literature. Increasing the spacing makes the flow asymmetric and induces vortex shading, which starting from last cylinder, preceding upstream. So, what exactly happens if we keep on increasing the if spacing is very low, the vortex shading occurs at the last cylinder only. If spacing is slightly increased, the vortex shading will occur at C5. So with further increase in the spacing, it will also be experienced by C4, C3, C2. When the spacing is very large, vortex shading is experienced by each and every cylinder. But when the spacing is very low, the vortex shading is experienced by the last cylinder only. That's what is observed in the literature as proposed by Liang et al. So similar flow regimes are observed for row of cylinders. So as observed for the row of cylinders are observed in this case also. However, the order of spacing of Reynolds number is reverse for these flow regimes. We will see that. We have worked with various Reynolds numbers like 80, 100, 120, 140, 150, 160, and these are the spacings which are used for. So total, we have calculated 68 simulations. This is the exhaustive work which we have done. I mean, 68 simulations means you can imagine each of some of the simulations have taken the time duration of around 15 days or 20 days or some in some cases even a month. Just sharing with you the results for if S by D is very low. You can see the vortex shading is occurring behind the last cylinder only, and it can be seen that all the cylinders are enveloped in one wake. And if you look at the variation of CL, this is for first cylinder, second, third, and so on for all the cylinders. You can see the sinusoidal signal is obtained when the spacing is very low. In the earlier case, at low spacing, the signal was chaotic. Here, at low spacing, the signal is synchronous. Except for this cylinder CL4, I don't know what has happened to CL4, but the results are not uh, as per the expectations. We have not gone into the details of why the results for CL4 are occurring like this, but then if you look at the results for drag coefficient also, this is CD1, and we have seen for six cylinder, PIP 4, 3, 2, and all other cylinders. You can see the signal is sinusoidal in nature. So this is synchronous in nature essentially. So flow behavior is synchronous at S by D equal to 0.5. On the contrary, in case of row of cylinders at S by D equal to 1 itself, the flow was chaotic. At 0.5, we are bound to get chaotic flow if the cylinders are kept in a row. Here is a power spectra which shows only one peak. Power spectra for three different cylinders is shown: 3, 2, 3rd, and 4th. Formation of a single wake behind all the cylinders. Small vortices between the gaps are seen here, but those vortices are just within the gap and are not being shared in the main flow. So that actually leads to a synchronous nature of the forces which is experienced by the bodies. A single peak in the spectra of a lift coefficient confirms synchronous behavior. The same behavior we have also observed for S by D up to 1.1. But for S by D equal to 1.2, 1.3, we have observed the quasi-periodic 1 type of behavior, wherein the signal is modulated now. Signal for lift coefficient is modulated. However, the time period of a secondary cycle is constant. Time period of a secondary cycle is constant. We observe two peaks. One is for secondary frequency, one is for the primary frequency. So that's a so this is occurring at 1.2, 1.3. The similar results are also obtained for 1.2. S by D equal to 1.3. So the flow here is quasi-periodic 1 in nature. What is quasi-periodic 1? That the time period of a primary cycle changes within 10%. However, the time period of a secondary cycle for consecutive cycles is constant, and that's a quasi-periodic 1. These are the vorticity contours for quasi-periodic 1 pattern. The vortex shading occurs essentially behind the last cylinder, and there is some fluid activity between the cylinders, but still there is no vortex shading occurring between the cylinders as such. Large size vortices are formed in the gap from the top and bottom of the vertical surfaces of the cylinders alternatively. So here the vortices are formed. These vortices keep on moving up and down, but these vortices are not shared in the main flow. And maybe this up and down motion of the vortices leads to alteration in the signal which I have shown here. But that alteration is systematic in nature. When I go ahead with S by D equal to 1.5 and 4, I mean, these are the results shown for 1.5 and 4, but we have done the simulation for 2, S by D equal to 2. In these all simulations, the Reynolds number is kept at 100. So we are not, so we have worked with a fixed Reynolds number to begin with. You can see the signal is highly modulated. This is, but still it is periodic. And such kind of flow, we named it as a quasi-periodic 2 type of a flow. And here we are showing, I'm sharing with you the vorticity contours for S by D equal to 1.5 and 1.4, or even the streamlines. You can see the vortices. I mean, there is a large motion of vortices in between the gaps that leads to development of secondary frequency. Some of the vortices even live at a S by D equal to 4. Then some of the vortices even are shaded from the body. So vortex shading actually has started as S by D equal to 4. We also work with S by T equal to 6. You can see the signal is highly chaotic in nature. There are large number of other peaks in the power spectra. We have worked with S by T equal to 10 also. So this leads to chaos. The moment at high gap ratio, the flow is chaotic in nature. At low spacing, the flow is synchronous in nature. On the contrary, in the earlier case, that is flow around row of cylinders, the flow was chaotic at small gap ratios, that is spacing, and synchronous at large gap ratio. So here, in this particular case, what happens? You see the the vortices are actually interfered by the downstream bodies present in the downstream region, and that leads to wake interference, and that wake interference actually causes the modulation in the nature of the forces experienced by the body. So, so wake interference is the major reason. The vortex is actually shared in the gap and the interfered with the downstream cylinder, leading to chaos. For row of cylinders, flow is synchronous at these gap ratios. So if S by D is 6, flow is synchronous if the cylinders are kept in row, vertical row. However, in the inline horizontal cylinders, it is chaotic. It's exactly reverse. Type of flow and the ranges are shown here. This is a summary of flow regimes at R equal to 100 for inline cylinder case. We have also tried to understand the effect of Reynolds number. At low Reynolds number, the flow is, we have worked with a fixed S by D 1.5. At low Reynolds number, flow is synchronous in nature. At Reynolds number of 120, it's quasi-periodic 1. It's Reynolds number of 160, it's quasi-periodic 2. If we further increase the Reynolds number, we expect it to be chaotic. So in the earlier case, at high Reynolds number, flow was synchronous. Here, at low Reynolds number, flow is synchronous. So if we have the cylinders placed in row and inline geometric position, we obtain exactly opposite results, and that's an important thing which we brought to the notice of the researchers, community of researchers. These flow regimes are also observed in the row of cylinders, but with change in the order with respect to spacing as well as Reynolds number. That's an important conclusion which we brought. I'm just sharing with you the flow regime map for inline square cylinder. You can see for a very small range of S by D, that is 1.1 and 1.2 and 1.3, we obtain quasi-periodic 1 behavior, which is shown by red dot here. The rest of all behaviors are the synchronous flow. Flow is synchronous, which is shown by a dark line. It is the dark symbol, dark black symbol, field dark black symbol. For very low spacing, for a very low spacing, we obtain synchronous flow. But flow is substantially quasi-periodic 2 in nature, and it is chaotic at high Reynolds number. It is chaotic at high Reynolds number and high spacing especially. We have also compared our results with that of the experimental work, which was carried out by one of the students, Rahul Patel. I acknowledge him. These are the experimental results obtained by using particle image velocimetry, and we have tried to plot the vorticity contours. These are our results, simulated results, and these are experimental results. You can see the vorticity contours are almost matching, so that indicates that the results which we have shared so far are in fact validated. In fact, those results are again. So this is a kind of experimental validation which we have provided for our results. So what I will do, I will come to the conclusion part of it. I mean, I have a lot of other work done, but it is not possible for me to share that work at this point of time. but the important conclusions which we have um, brought through this work are like this. And the flow around multiple bluff bodies have been studied to understand the flow physics of wake interaction and interference and its effects on flow regimes and parameters. Uh, Initiated with the study for flow around stationary row of cylinders, and it was extended to inline and V formation cylinders and row of transfer C, which I have not shared, of course, but I have shared with you the results which are extended to inline. The concept of development of secondary frequency, uh, that is the concept of wake interaction, was reported for the first time. The contribution of this frequency in the drag and lift coefficient is substantial and important while considering the fluid structure coupling. The physics of its development has been explained. The flow regime successfully identified for the row of cylinders and confirmed through study of inline cylinders. So we have identified 4 flow regimes. One is synchronous, second is quasi-periodic 1, third is quasi-periodic 2, and fourth is chaotic. In inline cylinders, the wake interference instead of wake interaction governs these flow regimes. So we have done the work with V formation also, but the conclusion for V formation and the other for oscillating cylinders, I'm not going to talk about. The study forms the basis for studying the flow around large number of cylinders in an array, which is proposed in the future. We have worked with array of cylinders also, but that has not been shared here. So thank you very much. I think I'm just close to 11:30. So I will take up some questions very quickly, if there are. Um, I know it's not really possible to cover the whole work within a short span of time, but I have tried to give you the glimpses of my work which I have done. So the purpose is just to tell you that a simple problem of flow around cylinder can itself be resolved, and I mean such a simple problem can form a basis for doing your research work, obtaining your PhD. If there are any questions, I will like to take those questions. There is a question by Professor Rana Robo. Please suggest the textbook. Yes, there is one textbook available on lattice Boltzmann method. I am not recollecting the name right now. I will get back to you on the name of the book. Is there any question, by the way? Is there any question? Am I audible or not? Am I audible?
Yes, sir.
No. If you have any question, please go ahead. What is your recent published article using FEM to solve the? We have recently published one work for flow through a twisted tape, wherein we have used a finite volume methodology. Of course, we use a software also, and flow through a pipe with a twisted tape. We publish in Journal of Fluid Engineering, published by ASM. Can you demonstrate techno to create the films? I mean, it's I can do that separately for you, but then it's not possible at this point of time because we are having short of. There's a question by Mr. Vinesh Gada. Welcome, Mr. Vinesh. Dr. Vinesh, welcome. Thankful to you for joining us. He is our next speaker. Yes, sir. Can you comment on about the computational typical time increase in the multiple cylinder simulation? Yeah, compared to single cylinder, time is almost fourfold or fivefold. I mean, I remember for single cylinder, we used to take 4 days to generate the data of around 10 lakh time iterations. But for multiple cylinder cases, it took more than 15 days, 15 to 16 days for a single case situation. If my Reynolds number is low, maybe we took lesser time, but for a large Reynolds number, we need to uh, do the fine meshing, and in that case the time required. And for multiple cylinder cases, especially inline cylinder cases, the domain size is very large, and because of that the time period required is very high. Time required is very high. So typical time uh, required for carrying out the simulation with six number of cylinders at S by T equal to 10, that was somewhere around 20 days or so. So compared to single cylinder, of course, the time required is, I mean, multifold, three, fourfold at least I can say. I hope, Dr. Gada, I have answered to your question. Can LBM use for high-speed compressible flow? Yes, it can be used. The LBM is a microscopic methodology, so it can be used for the high-speed flows also. People have started using LBM for high-speed flows. But of course, a different model has to be used. We have used a D2Q9 model. You need to make use of a three-dimensional model in that case. Is there any question? In LBM, there is a question LBM versus FVM. In FVM, the moment you change the configuration, you need to change the grid and grid. I mean, you need to do the grid generation again. I mean, you need to substantially change the uh, meshing. But here, meshing is a very simple. The other important thing is that in LBM, putting the obstacle is very easy. I mean, in a single two three lines itself, you can change the position of the obstacle in the code. So putting obstacle in the flow is very easy when we are using the lattice Boltzmann method. We can quickly change the configuration in lattice Boltzmann method, and that's why we prefer to make use of LBM. Is there any more question? If there are no questions, maybe we should stop this meeting. Thank you very much for your patience listening, and we'll be meeting for the next session at 12 o'clock by Dr. Vinesh Gada, who is already there, uh, and he will be speaking on Dr. Gada will be talking about the simulation of multiple flow regimes, two-phase flow, and applications. Uh, so we will meet at uh, 12 o'clock again. Thank you very much.
Thank you, sir.